Hi class, my name is Dr. Scott Adamson, and in this video we're going to look at the meaning of the area under a curve using a right-hand sum. Now this is the second in a series of two videos. In the previous video we examined this context using a left-hand sum. You should really watch that video first. But in this video we will continue on and investigate what this area looks like using a right-hand sum. Recall the context. We have a winter storm in northern Minnesota that was dropping on average 1.75 inches per hour for 8 hours. But what we understand is that storms usually don't drop snow at a constant rate over 8 hours. There's a varying rate. And so suppose the varying rate was given as we see here. Every 2 hours we were able to measure the rate of snowfall as shown in this table. And we have a graph of this situation. Now in this case, when we estimate the total snowfall, we're going to look at each of the 2 hour subintervals of time, but we're going to choose the rate on the right-hand side. So for example, in this first 2 hours, we're going to suppose that the snowfall fell at a constant rate of 1.75 inches per hour. So in that first 2 hours, we're going to choose the rate on the right-hand side of 1.75 inches per hour. And as we saw in the previous video, the area of this rectangle is just a geometric representation of the total amount of snowfall during those 2 hours. If snow fell at 1.75 inches per hour for 2 hours, we could compute how much snow has fallen. We're going to do that for each of the 2 hour chunks of time. In this next 2 hours though, instead of the left-hand rate, we're going to choose the right-hand rate. So from 2 to 4 hours, we're going to choose the rate at 4 hours of 2.5 inches per hour. Oops. Only for those 2 hours though. And so the area of this rectangle will represent the total snowfall during that 2 hour interval of time. From 4 to 6 hours, again, we're going to choose the rate on the right from 4 to 6, which would be the 2.25 inches per hour for 2 hours. And then for the last 2 hours of time, we're going to choose that right-hand rate of 1.5 inches per hour for 2 hours. So each of those 4 rectangles represents the total amount of snowfall during their representative 2 hour increment of time. So let's just one by one estimate how much snow has fallen each of those 2 hours. So in the first case, we used the right-hand rate of 1.75 inches per hour for 2 hours. We multiply to get the total snowfall. Again, in units, inches per hour for 2 hours will give us the total amount of snowfall, in this case, 3.5 inches. In the next one, using that right-hand sum, it was the 2.5 inches per hour for 2 hours. Would give us a total of 5 inches of snowfall. And for the next one, we use the 2.25 inches per hour for 2 hours, which would give us 4.5 inches of snowfall. And for the last 2 hours, we use the 1.5 inches per hour for 2 hours, which would produce 3 inches of snowfall. So in total, if we sum up all of these totals over the individual 2 hour increments of time, we will get an estimation for the total snowfall during the total 8 hours of time. So 3.5 plus 5, 8.5, 13, that would be a total of 16 inches of snowfall. So again, we have an estimate of how much snow has fallen. If we just take the average, it was 14 inches. If we do a left-hand sum, it was 14.5 inches. If we do a right-hand sum, it's 16 inches. We're just finding different ways to estimate the total snowfall. Right-hand sum, left-hand sum. Now, we could take it one step further, and instead of gathering data every 2 hours, we could gather data more frequently, thus getting even more accurate results. So you've now seen how the area under a rate of change curve geometrically, visually represents, in our context, the total snowfall over an 8 hour period. We've estimated it with a left-hand sum, we've estimated it with a right-hand sum, we use 2 hour increments of time, but these are just estimates. In fact, the snowfall rate could be theoretically changing all the time. So imagine, we're going to do a little theoretical experiment here inside of our heads. This would not be very practical to do. In fact, it wouldn't be practical at all. So this is just a theoretical experiment inside our heads, and it's like this. Imagine that we were able to somehow know and record snowfall rates at every instant in time. Rather than 2-hour increments, imagine we had infinite amounts of data. Instead of those 2-hour subintervals or those 2-hour intervals of time, imagine that we were able to shrink that down to infinitesimal intervals of time. In that case, here's what we would have. In a left-hand sum, we would say at time 0, we're going to find that snowfall rate, but we're only going to follow that rate for just an infinitesimal amount of time. Now I know in my drawing, I've drawn it, as big as I've drawn it, but inside of my head, I've drawn that rectangle infinitesimally thin. And we get to the next interval of time, and we find a rate from here to here using the left-hand side, but maybe we get a different rate, and we find the area of that rectangle. And then for the next interval of time, we get another rate, and we find the area of that rectangle, etc., 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 etc. And we do that infinitely many times so that these rectangles are infinitesimally thin until we get to that last subinterval of time. And in that last subinterval of time, we're going to choose that left-hand rate and find the area of that rectangle. So just imagine, inside of your brain, there are infinitely many blue rectangles here. They're infinitesimally thin. We're tracking the areas representing the total snowfall over tiny, just microseconds, even smaller than that of time. And we're going to sum them all up, like we did before, but instead of only 4 rectangles, we're going to have 4 bazillion rectangle areas to sum up. Now in this case, we're going to start with the first moment in time is going to be when time is 0, and then we're going to stop when we get to 1 less than that 8-hour increment, because that last, on a left-hand sum, that last subinterval of time will take us to the 8-hour mark. So imagine summing all of those up. Infinitely many. So in math, we have a way of expressing that. The Greek letter sigma is the letter we use to represent this idea of summing up. And what we're summing up are the heights of each of those individual rectangles, and the heights of all of those rectangles mathematically can be expressed using function notation. It's a f of t. It's f of t sub 0, f of t sub 1, f of t sub 2, f of t sub 3, etc., 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 until we get to, now there's going to be infinitely many of these, but we're going to get to that 1 less than the 8-hour mark. So we're going to have f of t sub 0, so when I is 0, we get that first rate. F of t sub 1, 2, 3, 4, 5, and we're just going to keep marching on until we get to 1 less than that 8-hour mark. Now, infinitely many, so we'll take the limit as n goes to infinity. We'll sum up those rates times the delta t. Now before, the delta t was the 2-hour change in time, the 2-hour interval of time. Now our delta t are just these infinitesimal changes in time. Practically 0, but not 0. So the total amount of snowfall could be expressed using this notation. Sum up the rate of snowfall in inches per hour times that infinitesimal change in time measured in hours. Inches per hour times hours gives us a total amount of snowfall in inches. Now we could also do that with a right-hand sum. Imagine in that first infinitesimally small subinterval, instead of choosing the rate on the left, we choose the rate on the right. And in the next subinterval of time, instead of choosing the rate on the left, we choose the rate on the right. And I'm just arbitrarily drawing these rectangles in to capture the idea of there is going to be some rate. And we would, again, for each subinterval of time, choose the rate on the right-hand side. Now these rectangles, again, are infinitely many, neither infinitesimally thin. I'm just trying to get my brain to think about what's happening here. So now I'm going to sum up the areas of all of those rectangles to get the total amount of snowfall over the 8 hours. So So I would keep doing this, in theory, inside my head. I would just keep doing this, and when I got to that last subinterval of time, since it's a right-hand sum, I would actually use the 8-hour mark, and I would say the area of that last rectangle would be the amount of snowfall in that last moment in time. So in this case, again, infinitely many rectangles, so we're going to take the limit as n goes to infinity, but now I starts at 1. Notice t sub I, t sub 1. Rather than starting here at 0, we're going to start at that first time increment. And then the second, the third, the fourth, the fifth, the sixth, the seventh, we're going to keep counting until we actually get to that last one, the nth one, at the 8-hour mark. So the rate, f of t, the function value, the output value of this function, the rate in inches per hour, gets multiplied by the amount of time that has elapsed, that infinitesimal amount of time measured in hours, inches per hour times hours, sum them all up, total amount of snowfall in inches. Left-hand sum, right-hand sum. But since we're playing this imaginary game, this theoretical game in our brain, imagine this. Imagine that there's infinitely many rectangles that are infinitesimally thin. Is there going to be a big difference between the left-hand sum and the right-hand sum, the left-hand sum and the right-hand sum? If we have a change in time that's so infinitesimal, the corresponding rate will be the same on either side. So when we theoretically have infinitely many rectangles that are infinitesimally thin, then what we say is that these two sums will converge to a single value. And we express that using this notation over here. This is called the definite integral. And the definite integral is accomplishing what our left-hand sum and right-hand sum was doing previously for infinitely many, infinitesimally thin areas of rectangles. So this symbol, this kind of elongated S for sum, we're summing up the output, the function values, those outputs were rates in inches per hour, times delta t, the change in time, which was that infinitesimal change in time measured in hours. So inches per hour times hours, sum them all up between A and B. In our case, between 0 and 8 hours. If we summed up the area underneath that curve, we would get the total amount of snowfall. Now at this moment, here's the best that we can say. The total amount of snowfall, as represented by this definite integral between 0 and 8 hours. That function f of t was the rate of snowfall function in inches per hour. That delta t, those infinitesimal changes in time measured in hours. What we can say is that is somewhere in between the 14.5 inches of snow we got with the left-hand sum and the 16 inches of snow that we got with the right-hand sum. Now in future videos, you'll find out how we can narrow that down and get a very precise measurement. But for now, we're going to leave it at this integral, this definite integral is going to produce a value somewhere between 14.5 and 16 inches.